Hi students, this is a video to go over some important details regarding calculating, significant figures, scientific notation, and density. So first let's start with when you're in the lab and you're collecting data, you're going to want to understand two words, accuracy and precision. Accuracy has to do with how close your data comes to a true value, an accepted value. Whereas precision is how close your measurements are, your data, to one another. That means reproducibility. So when you're looking at this dartboard, I think it will help illustrate what I'm talking about. In the first example, A, you notice that all of the darts are surrounding the bullseye. And the bullseye is where you want to be in a dart game. So the first one is high precision and high accuracy. The second one, on the other hand, all four pieces of data are close to one another, making it precise, but it has low accuracy because it's not hitting the bullseye. In the third example, it's neither precise nor accurate. The data is not reproducible. So keep those words in mind as you learn. Let's talk about something called sig figs, or significant figures. This is a key concept in chemistry. It has to do with, based on the lab equipment, what numbers do you record as your answer? And later when you go on, if you go on into AP Chem or into college chemistry, this will become an even bigger topic. You can find these rules anywhere. They're very common in chemistry. And mostly it has to do with which zeros count when you're keeping a number in the form that it's supposed to be in. So first, zeros at the end of a number or before the decimal point do not count if there's no decimal point showing. Here's an example, 12400. Looking at that, how many sig figs do you think there would be? We'll come back with that answer in a second. If the number is smaller than 1 and does have a decimal point, the zeros before the first number do not count. An example would be 0.045. So in these two examples, the first one, 12400, has three significant figures. The zeros at the end are only placeholders. They are not actually significant to the lab equipment, so they're not reported as sig figs. Here, the same, only two, the 4 and the 5. These zeros, again, are placeholders. Let's continue with which zeros count. Zeros in between other zeros are significant and they do count. Look at the example 1002, 1002. The two zeros in the middle help to determine the size or the magnitude of that number, so they are important. Also, zeros at the end are important as well. 45.8300. These zeros are important because they actually show you the accuracy of the equipment. These are called final zeros. Not placeholders, but final zeros and in-between zeros do count. With that, the first number here has 4 significant figures, and the second number here has 6 significant figures. Keep in mind the last digit in data collected is always an estimate. Now, a way to remember these things is known as the Atlantic-Pacific rule. The Atlantic-Pacific rule. So look at what would be a shape like the United States and follow the rule. If the decimal point is present, we start at the Pacific side. If the decimal point is present. And then from there, we count and look. If the decimal point is absent, we start at the Atlantic side. And that would be, sorry, I'm bouncing around here. That would be this side of the United States map. So this is how we do it. If we have a decimal point present, we start from the Pacific side, we draw a line through any leading zeros until we get to the first whole digit non-zero number. Then we count all the sig figs from there. Everything else is significant. Let me show you a couple of examples of how this is done that will help you understand the Atlantic-Pacific rule. So let's look at the first one, 910 meters. Decimal point absent or present. I don't see it. It's absent. Go to the Atlantic side. That's the right side of the number. Cross out the zeros that you see. Begin counting at the first whole number digit. So we're going to count the 1, we're going to count the 9. 2 significant figures. The second one, decimal point absent or present? It's present. So I'm going to start at the left side this time. That's the Pacific. Cross out all zeros, begin counting at the first whole number digit, and count the rest. 1, 2, 3, 4. 4. This next one, decimal point present. Start at the Pacific. There are no zeros to cross out. That means every digit is significant in this measurement. The next one, decimal point present. Cross out the first ones. Start at the 6. Count the rest. I hope you're catching on using the Atlantic Pacific rule. Something you need to understand is that counting numbers such as how many eggs are in a dozen are exact figures. They do not have significant figures. Significant figures applies to calculations and data collection. Okay? So counting numbers have infinite significance. So we say infinitely many sig figs. On the other hand, a measurement like the paper is going to have sig figs. Okay? This is an important skill. It continues on with you if you go into AP Chem and college chemistry. How do you calculate with sig figs? A lot of students ask, how do I round off this number? Well, keep in mind the very last sig fig is always an estimate, but it's still part of the sig figs. When you add and subtract, what you do is you line up the decimals, round the numbers to the same digit place, and when the math is done, you end up with the proper answer. Here's an example. Let me move my little person down. Okay? I'm getting in the way. Hold on, sorry. That is not helpful. Escape. Okay. I need this to go out of here. I think I'm going to close it. Sorry. Sorry for the trouble, friends. Okay. Back to adding and subtracting. So you line them up. In this case, I didn't round them yet. I just lined them up. I did my math. And then I looked to see which one had the least decimal places, and I rounded it to that number of decimal places. Go ahead and try this one. And as you try that one, you can check your work. There's the answer. What about when you're multiplying and dividing? When you're multiplying and dividing, it's a little different because you don't have decimal points to line up. You do the math. You count the sig figs in the original numbers, and you always record your data to the lowest number of sig figs. Your answer can't be more accurate than your least significant piece of data. So these two numbers, here's how I did it. I first counted to see how many sig figs each had. I used the Atlantic Pacific rule. I found 3 and 4. That means my answer is going to be rounded to, 3. So then I did the math, and then I rounded this answer to 3 sig figs. Here's one for you to try. And when you're done, check your answer. Scientific notation is something we use a lot in chemistry. It's a way of representing a number that might be very, very large or very, very small. And we represent it basically in a digit, a multiply times sign, and a 10 to some power. Now the way you do this is based upon the number and how many places you had to move it. The direction you move it is what determines whether it's positive or negative. If you look at my box here in this little graphic, you see a number like 3250 and then another 6 zeros. Take the decimal from the end, move it all the way behind the first whole number digit. It turns out to be 9 spaces. We had to move it to the left. Therefore, the number ends up being 3.25 times 10 to the 9th. Notice moving to the left is a positive exponent. On the small numbers that have a decimal on the left-hand side, again, you're going to move all the way behind the first whole number, and then you're going to use a negative exponent to represent those. Here are 4 examples. Let's go ahead and try them and check yourself. Hopefully those are making sense to you. Again, if you move it to the left, it'll be positive. If you move it to the right, it'll be negative. Let's talk briefly about density. Density is how heavy something is for its size. It's the ratio of mass to volume, or mass over volume. So as an equation, D equals M over V. Something you should know about density is that density is known as an intrinsic factor of matter. It's always the same for a pure substance, no matter what. The mass over the volume will always equal a constant. A few things to know: gold has very high density, air has very low density. And when you look at this little gradient here, you can see that the density of various items determines whether they will float on each other or sink with each other. Something that is more dense, has a greater density, will sink below something that has a less or lower density. So whether or not floating or sinking is about density. When you calculate density, the units tell you how to calculate. The units are always going to be a mass unit over a volume unit. So you'll see things like grams over milliliters, grams over centimeters cubed. And then obviously, don't forget, 1 milliliter and 1 centimeter cubed are actually the same volume. So let's try an example. Here's a problem, and you read it and you notice 11.2 grams are given and 23 milliliters. D equals M over V. Plug into the equation and solve for these two. Give them a try and let's see how you do. So here's how you do this one. Plug in the mass, plug in the volume, do a simple dividing, and that's your answer. The units are not going to cancel because grams mass is a different unit than volume. So they just stay there and they become the unit of your answer. Try the next one and check yourself. Here's your answer. Water is a very common substance, and the density of water, you should put a big mark on this, highlight this in your skeleton notes. 1 gram equals 1 milliliter. It's important to know that for water. So anything more dense than that will sink below at the bottom in water. Anything less dense than that will float in water. Also keep in mind from our previous work, 1,000 grams equals 1,000 milliliters, which also equals 1,000 centimeters cubed, which just happens to equal a liter. Taking a look at this table, apply what you just learned to answering these questions. Pause and then check yourself when you're done. The most dense liquid here is mercury. The one with the greater mass, in these two, you have to look at the density. A greater density would mean a greater mass because their volumes are the same. Does ice float or sink in turpentine? I don't know. Does ice have less density or more? The answer is more. It will sink. Here's a few things for you to try. With each one, you should pause, do your work, and then check. The answer is here. So on this one, you put the mass over the volume, you'll solve for the density. Don't forget to show your formula, you're plugging in, and you're solving. So here's something you need to pay attention to. Volume, as you know, can be calculated based upon a geometry formula from math, length times width times height. You can measure it in a cylinder, and sometimes you have to use liquid for an irregular solid to put it in the liquid. Let me show you some examples of this. Let's say you're given a geometric shape and you need to find the density. You're going to need to use the mathematical formula to find the volume. First, you'll do that. So go ahead and use that hint, solve it, and then come back and check.
Landon Christie to the front office, please. Landon Christie.
Sorry,
to the
friends.
front office.
The answer for this one is 2.7 grams per centimeter cubed. And here's another, check yourself. On this one, you're putting an irregular solid or regular solid into a graduated cylinder filled with water. And if the water went up this much, what is the density of the object? You're right. You need to find the volume that is displaced. This is called water displacement. If the water goes up when you put the item in, the difference in the water level becomes the volume of the item. Now you're going to use that to solve the answer. Check and see, did you get 2? And that, my friends, is what you need to know for right now. Practice and continue to learn.